Hello everyone, myself Mohan Gowda. I'm currently studying electronics and communication engineering from SVC. Today I'm going to be making a video on the subject network analysis, and today's topic is nodal analysis and mesh analysis. Welcome to this comprehensive guide to nodal analysis and mesh analysis, two fundamental techniques in circuit analysis. These methods are crucial for understanding the behavior of electrical circuits from simple resistive networks to complex systems involving capacitors, inductors, and other components. We will explore the core principles of both techniques, outlining the step by step procedure and providing illustrative examples. Understanding nodal and mesh analysis is essential for electrical engineers, allowing them to analyze circuit performance, troubleshoot problems, and design efficient and effective systems. This guide will equip you with the knowledge and skills to confidently apply these techniques in various contexts, including circuit simulation and practical applications in real world scenarios. Introduction to circuit analysis techniques. Circuit analysis is a foundational aspect of electrical engineering, providing the methods to understand and predict the behavior of electrical circuits. It involves systematically determining various electrical quantities such as voltage, current, and power at different points within a circuit. This understanding is critical for designing, troubleshooting, and optimizing electrical systems. The complexity of circuits can range from simple resistive networks to intricate systems incorporating a variety of components like capacitors, inductors, and operational amplifiers. To efficiently handle this complexity, engineers utilize various analysis techniques, with nodal and mesh analysis being two of the most prominent. Nodal and mesh analysis. Nodal analysis and mesh analysis are two powerful and widely used methods for analyzing electrical circuits. These techniques offer systematic approaches to solving for unknown voltages and currents within a circuit. Nodal analysis focuses on the voltage at the nodes junctions of a circuit. By applying Kirchhoff's current law at each node, a set of equations is generated that can be solved simultaneously to determine the node voltages. Mesh analysis, on the other hand, utilizes loop currents circulating around closed paths, meshes, within the circuit. Kirchhoff's voltage law is then applied to each mesh, creating a system of equations that can be solved for the unknown mesh currents. The choice between these methods often depends on the specific circuit topology and the desired unknowns. Advantages and limitations of nodal analysis. Advantages. Nodal analysis simplifies circuit analysis by focusing on node voltages, which are easier to determine than currents. It eliminates the need for separate equation for each branch, making it efficient for complex circuits. Limitations. Nodal analysis can be challenging for circuits with a large number of nodes, requiring complex equations. It may also be less intuitive to grasp for beginners, requiring a clear understanding of Kirchhoff's current law. Formulating nodal equations. Identify nodes. Start by identifying all the nodes within the circuit, including reference nodes, ground. A node is a point where multiple circuit elements connect. Apply Kirchhoff's current law. Apply Kirchhoff's current law (KCL) to each node. KCL states that the algebraic sum of currents entering a node is equal to the algebraic sum of currents leaving the node. Express currents. Express currents is a term for node voltages and resistance using Ohm's law. I is equals to V by R. For example, if the current flows from node A to node B, then the current can be expressed as VA minus VB by R. Solve equations. The resulting equations form a system of simultaneous equations that can be solved for unknown node voltages. Solving nodal equations, matrix form. Rewrite the nodal equation in the matrix form where the unknown node voltages are represented as variables and the coefficients are based on resistance. Matrix methods. Use matrix methods like Gaussian elimination or Cramer's ruler to solve for the unknown node voltages. Solution. The solution to the matrix equation provides the values of all the node voltages, which can then be used to calculate other circuit parameters like branch currents and power dissipation. Advantages and limitations of mesh analysis. Advantages. Mesh analysis is often preferred for circuits with fewer loops than nodes, making the formulation and solving of equations simpler. It's also more initiative for understanding current flow in the circuit. Limitations. Mesh analysis can be complex for circuits with a large number of loops, leading to lengthy equations. It can also be challenging to analyze circuits with dependent sources, requiring additional steps and careful consideration. Creating mesh equations. Identify loops. Identify all independent loops in the circuit. A loop is a closed path that does not pass through the same node twice. Assign loop currents. Assign a clockwise current variable to each loop. It's important to note that the direction of current is arbitrary and not, but consistent. Apply Kirchhoff's voltage law. Apply Kirchhoff's voltage law to each loop. KVL states that the sum of voltage drops around a closed loop is equal to zero. Express voltages. Express voltage drops in terms of loop currents and resistance using Ohm's law. V is equals to IR. For example, if the current flows through a resistor R, the voltage drop across the resistor can be expressed as IR. Solving mesh equations. Matrix form. Write the mesh equation in matrix form similar to nodal analysis, where the unknowns are loop currents and the coefficients are resistance. Matrix method. Solve the system of equation using matrix method like Gaussian elimination and Cramer's rule. Solution. The solution will provide values for the loop currents which can be used to calculate voltage drop, branch currents, and power in the circuit. Comparison of nodal and mesh analysis. Nodal analysis. The advantages: fewer equations for circuits with more nodes than loops. Limitation: can be complex for circuits with many nodes. Applications: circuits with many nodes and fewer loops. Mesh analysis. The advantages are fewer equations for circuits with more loops than nodes. Limitations can be complex for circuits with many loops. Applications: circuits with many loops and fewer nodes. Applications and examples. Nodes have numerous applications in various electrical circuits, including DC circuits. Analyze voltage and current distribution in simple series and parallel circuits, circuits. Analyze circuits with alternating current like power grids and household wiring. Electronic circuits. Analyze complex circuits involving transistors, operational amplifiers, and other electronic components. These methods provide a structured approach to analyze circuit behavior, calculate key parameters, and understand the operation of various electrical electronic devices.